Today I'm going to talk about the purpose of routing, and then I'm going to move on to some basic routing concepts. There's a fair amount of ground to cover, so let's go ahead and begin this session. First up is the purpose of routing. The basic purpose of routing is to connect different networks together to allow them to communicate and pass data traffic between them. Most often, routing protocols are how networks determine where to send network traffic. That's the routes that they will take. And these routing protocols build maps. Actually, they build routing tables, but we'll get to that later, that they use for directing network traffic. Routing is what makes this interconnected world function as well as it does. Networking would be pure chaos without it, as we'd have no idea where to send traffic. Now let's move on to some basic routing concepts. First up is static routing. Static routing uses administrator-defined routes. Each router in a static routing configuration must contain the route. A static route from router A to router B requires that router B has a static route back to router A in order for two-way communication to take place. If we had a static route from A to B and B didn't have one back to A could send traffic to B, but B could not send traffic back to A. Now, static routing is easy to set up in small networks, but it's not so easy to maintain. Networks change all the time. With static routing, when a change occurs in routers, the administrator has to go around to each router and implement that change. Then there's dynamic routing. This is where routers use protocols in order to determine the best route between two networks. The administrator determines which protocols will be used on the routers. In order for the routers to communicate, they must all be using the same protocols. There is an exception to that, and that's route redistribution. An administrator can configure a router to take one dynamic protocol and transform it into a different routing protocol to be used from that point on. This is the only case when routing protocols can be different across a network. Routing protocols can be stacked within a router. That means that there can be more than one dynamic routing protocol programmed into a router. Dynamic routing is very fluid and dynamic, and it's what makes possible today's interconnected world. The next concept is the default route. The default route is the direction that a router will send network traffic when there is no known route in the routing table. The default route is assigned by an administrator. It is usually a designated interface on the router, or it is the next designated next hop interface. Then there is the routing table. The routing table is a list of known routes to all known networks from the router's perspective. It is established by an administrator when static routing is used. It is dynamically built by routing protocols when dynamic routing is employed. Each routing protocol maintains its own routing table. Different routing protocols may have different routes to the same network. The loopback interface is an administratively configured logical number assigned to a router to ease administrative functions or routing processes. Often the loopback interface is assigned in an IPv4 address format even when IPv4 isn't used on the router. Many routing protocols have been designed to take the loopback interface into account when performing administrative functions. The loopback interface may be completely logical, or a physical interface may be assigned to be the loopback interface. Let's move on to routing loops. A routing loop is a possible problem that can be created if interconnected routers have a breakdown in their routing algorithms. When a routing loop occurs, network traffic keeps looping through the routers until some system or mechanism breaks the cycle. Routing loops can create network congestion or even bring down a network. Routing protocols use multiple methods to prevent routing loops from occurring. One of the main methods that they use is what's called the time to live field, or the TTL field. The TTL field keeps track of how long that packet has been in existence and how far it has traveled, and after a specified amount of time or distance, it will inform the next router to drop it. This helps to prevent routing loops. That concludes this session on the Introduction to Routing Concepts, Part 1. I talked about the purpose of routing, and then I moved on to some basic routing concepts. Today I'm going to be talking about routing metrics, routing aggregation, and then I'm going to conclude with a brief discussion on high availability. We have a fair amount of ground to cover, not a whole lot of time, so let's go ahead and begin this session. Of course, I'm going to begin by talking about routing metrics. It is quite common for there to be more than one route available to a remote network. Routing protocols use metrics to determine which route is the best route to reach those remote networks. Each routing protocol will use its own set of metrics in determining which routes to which networks are placed in its routing table. The same basic metric may be used by different routing protocols, but when this occurs, the metric is usually implemented in a different manner through the use of different algorithms. The first metric that we're going to discuss is the hop count. The hop count is the number of routers between two endpoints. This is determined from the sending router's perspective. The maximum transmission unit, or MTU, is another metric that is used by routing protocols. The MTU is the maximum allowed size of a packet measured in bytes that's allowed through an interface. The standard MTU for Ethernet is 1500 bytes. Packets that exceed the MTU must be fragmented into smaller pieces, leading to more packets, leading to a slower connection. Bandwidth is another common routing metric. Bandwidth is a measure of the speed of the network connection. The speed is commonly measured in either kilobits per second, megabits per second, or gigabits per second. Another common metric is latency. Latency is a measure of time that a packet takes to traverse a link. When latency is implemented by routing protocols, the total amount of latency or delay to go end to end between 2 points is what is used in the metric. The administrative distance, or AD, is probably the most important metric that's used on routers. The administrative distance is the believability of a routing protocol's advertised routes. Different routing protocols are considered to be more believable or trustworthy than others. Routers use the AD to help determine which routing protocol to use when more than one protocol is installed on the router. The lowest AD of an advertised route will determine the protocol that's used. There are some common standard administrative distance. First up is the directly connected route. That's a direct link between two routers. That has an AD of 0, and it is the most believable or trustworthy of routes. Next is the statically configured route. It has an AD of 1. External Border Gateway Protocol has an AD of 20. It's still fairly trustworthy. Internal EIGRP has an AD of 90. It's not as trustworthy as BGP, but it is more trustworthy than OSPF, Open Shortest Path First, which has an AD of 110. ISIS has an AD of 115, so not quite as believable as OSPF, but more believable than RIP, which has an AD of 120. External EIGRP has an AD of 170, An internal BGP, and I've never seen internal BGP used, has an AD of 200. Now, if you see an administrative distance of 255, that means that that route is not believable at all. As a side note, the AD can be set by an administrator. So if you are running both OSPF and ISIS on a router, but you want ISIS to be used, you could actually set OSPF's AD to a higher number than ISIS, and then ISIS would always be used before OSPF. Now let's move on to route aggregation. Without some mechanism put in place, routing tables would soon become very large and highly inefficient. Through careful planning, network administrators use a process called route aggregation to condense the size of routing tables. They do so through the use of classless interdomain routing, CIDR, to summarize routes to different networks. Route aggregation is common in networking. Let's take a look at an example of route aggregation. Suppose we have a router that has the following networks on its serial 0/1 interface. It has 10.1.1.0/24 known on that interface, 10.1.17.0/24, 10.1.32.0/24, and 10.1.128.0/24. All of those networks are known to that interface, that S/0/1 interface. These routes are what are known as contiguous routes. They're all in a line. They can be summarized or aggregated by a common CIDR entry in the routing table. They could all be summarized by the following entry, 10.1.0.0/16. Now there is a warning about route aggregation. Route aggregation takes careful planning during the network design phase. That above example would not work if the serial interface 1/1 on that same router was connected to network 10.1.2.0/24, because that new network makes those networks on the 0/1 interface non-contiguous networks. All the known networks are no longer all in a row. This leads to the fact that the routes could no longer be aggregated or summarized. Let's conclude with a discussion on high availability. Part of a network administrator's job is to ensure that networks remain up and active for the maximum amount of time. In an effort to ensure that networks don't go down, administrators often remove single points of failure. A single point of failure in a network is the point where a single failure will cause the network to cease functioning. Network administrators often use high availability techniques in order to remove those single points of failure. An example of a high availability technique is the use of redundant links to outside networks. Hot Standby Router Protocol, HSRP, is a specific example of a high availability technique. HSRP is a proprietary Cisco method of creating a fault-tolerant link using two or more routers with connections outside of the local subnet. The two routers are connected together as well as having connections outside of the local network. A virtual IP address is created and shared between the two routers. Devices on the network are configured to use that virtual IP address as their default gateway for packets leaving the network. If a single router goes down, the link outside of the network is still available. Another high availability technique is Virtual Router Redundancy Protocol, VRRP. It is an IETF, Internet Engineering Task Force standard that is similar in operation to HSRP. That concludes this session on the Introduction to Routing Concepts, Part 2. I discussed some routing metrics, Then I moved on to route aggregation, and I concluded with a brief discussion on high availability.